Sam.
Then she would, yeah.
She sings it with us.
Oh, really? Sounds like it's great.
It is. She kills it.
Yeah.
We played it.
Yeah.
I do. No problem. Do you have a roommate? I do. Here. Oh, okay. She's always over in your door. Yeah. Because she's got a lot of friends there. I see her. Yeah. She picks a dorm where she's gonna live at besides her own. And she's every year, it's like, yeah. That's how I met her my freshman year. I was in Curtis West and she was always in Curtis West. Wow. That's good that she's social. She's also very social. Hi Liz.
Wow.
Your freckles look great today.
Thank you. I tried.
Do your freckles get more prominent in the sun during summer?
Super fresh on me.
Next eyebrows look great today.
Hi.
I look great today.
Eyebrows on me.
Yeah.
No, I really appreciate that. Thank you.
She was in the freshman year.
Yeah, it's just
Like, big, cycle fit.
and you grew up. They look really good.
It's because, like, it's full Italian, natural, like, Mediterranean, everything.
This is good for faces. So yeah.
I'm so glad, like, thicker eyebrows get in style now. It's like, sometimes I feel like there's angry caterpillars on it.
Oh no.
Yeah.
It's definitely really hard because before I went to, I only had 2 days a week. So this morning I went to Yes, Walmart, Target, and Walmart. And I could only get 9. I said that's it.
Yeah. No. Oh. God, so many compliments today. Not yet. I went through this dilemma where, like, I
did after. I don't know.
enough
She said like 5
the amount of songs
today.
that I buy, and then, like, I rack up like hundreds of songs I want to buy, and so then when I finally do, they're like 3, so I don't know which ones to buy. I'm like, I have so many songs, I don't know which ones to buy. So literally, I bought like a $25 gift card like 2 months ago, and I have purchased 2 songs. So I don't know which ones are the best ones, which ones do I want to listen to all the time. It is a hard decision.
That's why I just
Like, I use Spotify. I have like my playlist of like all the songs I want to buy. It's like 135 songs long. Like it's so big. Yeah, I hate the ads. Yeah, I did not bring my laptop tonight because I did so hard. Yeah, I figured it was another response to see. See, I hate, I don't think it's like the notebooks, my pencil, or my left-handedness that makes my notes look like this. Yep. Depending on the, like especially like ballpoint pens.
take it all over your
Oh. It's hard. It's hard. Well, see, the thing is, when I was little, I couldn't decide which hand to write with. I like switched hands all the time. Yeah, I was very obsessive. my parents sort of decided for me. They're like, you're going to be stronger in your left hand, so you're going to do everything with your left hand. So I was like, thanks, Mom and Dad.
Now when your mom gets you
Well, my mom probably should have been left-handed, but she's both in there with
Hi, Madison. Okay, we've got 12:30, so why don't we get started? Good afternoon, S&P. Welcome to Monday. Welcome to the start of audition. Lots of announcements today. First, I'm reeling a little bit. Just a few minutes ago, I found out that I had an article accepted, and I'm really ecstatic. So I'm going to be a little bit scatterbrained today. I'm really not so happy for me as I am for my student who worked very hard. Some of you might know this student. His name is Andrew Clement. Does anybody overlap with Andrew Clement? He graduated from here in 2013, and he and I spent his senior summer working together on an article. And we've spent a lot of time with a lot of reviewers having revision after revision. Then they suggest this experiment, we run it. They ask us to tweak that, we tweak it. And they say, maybe we changed our mind. Maybe we don't need that experiment after all. Well, 20 minutes ago it was accepted. So congratulations to Andrew, graduate of this class. Okay, lots of other announcements today. So let's just remind ourselves that this coming Wednesday we'll have another TED Ed, just like you had a TED Ed for today. Today we were going to be doing a TED Ed on the acoustics, generally speaking, from a physics perspective, just to understand what the stimulus is. And Wednesday will be more of a biological day for us, okay? So same kind of a thing, a TED Ed, just like usual. That's what we'll be doing on Wednesday. To look ahead to the next day, we will have Dr. Stephen Mayer joining us. And I have this little one, and there's the big one. You see these all around campus and all around this floor. Especially, Stephen Mayer is coming to us from the University of Colorado at Boulder. And he is a National Academy of Sciences professor, so he's way up there, very distinguished person in the field who's been working for many, many decades on the intersection between psychology and biology and neuroscience, and I think he's going to have lots of great things that will be of interest to you. So the first talk is going to be Thursday night, and that'll be in Burton Morgan's lecture hall, all the way downstairs. In fact, both of his talks are going to be all the way downstairs in Burton Morgan, and that's going to be at 7:30 on Thursday. Stress, resilience, and the prefrontal cortex. So I think that'll be really quite interesting. And that's going to be geared for a more general audience. We have invited the entire town to come in. We have it advertised on our website. So this will not presuppose a lot of information about psychology. The next day, he'll be doing another talk. We're very fortunate to have this 2-day talk sponsored by the Cantor series. And that second talk will be entitled Aging and Cognitive Vulnerability, the Role of Microglia. Who remembers hearing about glia? Okay, can you remind us what glia are?
So they have a couple of different roles, but they're like the support cells. They're not like, they don't transmit the information, but they, some of them like form the myelin around the axons and neurons, or they like have like scavenger.
Yeah, right. So lots of supporting roles for us, and he's going to be talking about that on Friday, and that's going to be just a little bit more specific, and that is geared for undergraduates like you who are majoring in psychology. So he will presuppose a little bit, maybe that you've had Psych 100 or something like that, whereas the Thursday night talk is for what we call the PBS audience, right? These are smart and intellectually engaged adults, but you can't presuppose any particular kind of training, okay? So we're delighted to have that coming up on Thursday and Friday. Okay? Friday in this class, what we're going to be doing is having our conversation about our next Power and Justice paper, right? So we've got that, and we handed that out a while ago. I'm very grateful to a student who let me know that one of the links was not working, and then I sent an email out immediately after I found out on Friday that the link for the Deaf President Now movement had not been working, but I sent you 2 in that email, and they're also now available on Blackboard. Did anybody try those links? Okay, and they are working? Is that working? Okay, so any combination of those will be fine. I really wanted to get your feel for the very interesting Deaf President Now movement at Gallaudet University. I believe that we play them occasionally. I don't know if we played them in recent years. They're not that far away from us geographically. They're in Maryland, so you can kind of get there on a bus ride. It's kind of a long bus ride, but you can get there. And occasionally, we do play Gallaudet in sports. Do we have any athletes here that have traveled to Gallaudet to play them, or have they visited us? Okay, I'm not sure that we do that every year. Okay. Interestingly, they are deaf, and I'm told that that's where the football huddle started. Right? They would be in a huddle so they could conceal their hand signals to one another. That's how the players would be speaking to one another using sign language. So they wanted to conceal that, and that's where the football huddle had started. So this is them getting a new president, and they want a deaf president. Very interesting social issue, and very appropriate because we're now setting the stage for our conversation in audition. Okay, so one other thing, while we're talking about the power and justice issues for Friday's paper, you might remember that toward the end of this semester, we're going to spend the entire last week building YouTube videos. We'll spend a couple of days on that Monday and that Wednesday preparing those. And then on that Friday, it'll be the last day of class, we will be up in 505, and I'll have you in small groups, and we will shoot a video of you making a power and justice presentation that we can make available to the entire world. So we spent a semester consuming information, now we're going to generate some information. And you are the second class to do that. My 2013 class had also done that. The years prior to that, we had done poster sessions, but I think the YouTube videos are more fun. How many people have done YouTube videos before? Either in your personal lives or maybe in other classes you've created? And how many people have not done YouTube videos? Many of us have not, a few of us have. I won't show you the full-length video because it would take most of the session, but I thought I would show you one group. Does anybody here know Harshita Pancholi, who graduated just this past May? And does anybody know Briella Bear? Okay, so this is Harshita and Briella doing their two-group presentation on the semester end power and justice issue and disability. Okay, so I'm going to see if I can dial them up. We'll take a look at, they're on for only about 4 minutes or so. I'll make this nice and loud. And this will give you a flavor for what you're going to be doing during the last week. Okay? Again, on power and justice issues.
This is Priya.
There we go. Stigmatizing disability.
Hi, I'm Harshita. This is Priyala, and I'm very here to present on stigmatizing disability. As you know, it's an unfortunate truth of today's world that stigma is present everywhere. It might be a unique revelation to some of you that even within stigma, there are different types, and people often prefer one over the other, as awkward as that sounds. So there was a study done by Albrecht et al. In 1982, and they hypothesized that there were these two different types of stigma, deviance and disability. Deviance is a deviation from social norms. It's usually a social condition, whereas disability is an actual physical difference, which is often functionally incapacitating as well. To test this, they took a list of 27 different stigmatizing conditions and ran a factor analysis on them, and the results gave 4 main types of stigma. Group 1 had severe, visible, and disabling conditions such as paraplegia or amputation. Group 2 had mainly the deviance type of conditions such as mental illness, drug addiction, alcohol addiction, etc. Group 3 had...
Excuse me.
Well, they were incapacitating as well. To test this, they took a list of 27 different stigmatizing conditions and ran a factor analysis on them, and the results gave 4 main types of stigma. Group 1 had severe, visible, and disabling conditions such as paraplegia or amputation. Group 2 had mainly the deviance type of conditions such as mental illness, drug addiction, alcohol addiction, etc. Group 3 had...
Okay, let me try to go ahead.
1, they have to deal with the disability itself, and for 2, they have to deal with the stigma that other people put on it. As you can see in this image, this artist is struggling not only with the disease, but with shame. That's a social stigma that's placed on it. Based on this, I also found another study by Corrigan and Watson in 2002, which looked at the effect of stigma on work. And they came up with a very disturbing result. They found that there is a vicious cycle that goes on with the people with mental illnesses. First of all, they have a psychiatric disability, which they struggle with. And as we have seen, this psychiatric disability puts a social stigma on them. This social stigma usually leads to prejudice, which then leads to discrimination and leads to unemployment. A long period of unemployment then would cause the most dangerous of them all, that is self-stigma. This is dangerous because in addition to people putting stigma on them, these people are stigmatizing and discriminating against themselves. Considering that this is a mental illness, the chances are great that it probably worsens their psychiatric disability and the cycle continues. The way I see it, the only place that we can actually stop this cycle would be social stigma. That would be up to us to do. And now, Briella is going to tell you about why the social stigma occurs.
Okay, so as Harshita was just discussing, we do know that stigma against the disabled definitely is something very real. And so the same paper by Retinal from 1982 looked into why it is that this stigma exists. So based on how participants answered, they found that the reason for social distance from the disabled was due to a fear of social disruption. So to further break that down, they found that the majority by far, so 82.8% of participants, said this was because of the general ambiguity of the situation, meaning a general awkwardness of not knowing how to interact with someone who was disabled. Another 7% said it was because of guilt or pity. 4.7% said a threat to social well-being. 3.9% said a physically offensive reaction to the disabled, and 1.6% said they felt a threat to physical well-being. To go along further with that, they also assessed the social distance, so in other words, the stigma against those who had severe, medically severe yet not visible disabilities such as cancer or heart disease or asthma, as Harshita talked a little bit about, and in comparison to those with deviant qualities or disabilities, and they found that people most often associated with those who had these severe yet not visible disorders. So this suggests a connection between visible conditions and stigma. So this is a cartoon by a British handicapped artist, Crippen, and I think this very well illustrates the stigma. I don't know how well you can see this, but they're asking, do you think they take sugar? This is a group of disabled people. So instead of simply asking as you would to anyone, they have that fear of just the awkwardness of how not to interact with the situation. Another study by Goldstein and Johnson in 1987 assessed how far the stigma reaches based on those who associate with the disabled. So they interviewed college students about the perceptions of an able-bodied person who is dating someone who is physically disabled. And they found significant results that college students likely view the able-bodied partner as someone who is trustworthy and nurturing, but they also were less likely to view them as athletic, sociable, or intelligent. So that suggests that our stigma reaches far beyond those who are disabled, which is bad enough. So we have reason to believe that a lot of stigma is subconscious, so it's important just to be aware of the stigma that you may or may not realize that you have. So remember to check your stigma.
Okay, and then we were on part 5. We won't watch the whole thing, obviously, but I wanted to give you 4 or 5 minutes so that you could see the rhythm that you will have for your power and justice presentations toward the end of the semester. You'll be working in a small group. Your group will put together one PowerPoint presentation, and then you'll take turns doing slides or presenting slides to the camera, which will probably be that iPad. And then we'll put those all up on YouTube. And then I'll string them all together, and we'll have something like maybe a 40 or 45-minute presentation for the entire class, but any one group might be going only for 5 minutes or something like that. People okay with that? Yeah? Okay, really good. So I look forward to the video that we're going to make, and why don't we now get back to what we're doing for this week. And we're picking up this week on audition, and we were going to make the connection between vision, which we have been doing all this time, over to audition. And just as a bit of a connector, I thought I'd remind you that we studied lots of different features in vision. After we talked about the physical properties of light and we talked about the physiology, we did a whole section on color perception as a feature. And then we did a whole section on form perception, and that also had the face component as well. And then we had a whole section on depth perception and so forth. So these are different features that we were looking at. One other feature that you might think about is the feature of simultaneity, and that's what we described on Friday. We were talking about how we can measure the precision with which the visual system has timing characteristics, and we can look at the simultaneity judgments that people make, or the temporal order judgments might be another variety, but the simultaneity is what we were looking at last time. I got the sense that as we were getting late into the session, we were all getting a little bit tired, and we might not all have been on track with that. So I thought I'd do just a quick review of a couple of the main points from that, and then we'll go into today's TED Ed, just so that in case something comes up on a exam or the final exam, we would have good familiarity with the main points. There's a lot of details in that article that we don't need to concern ourselves with. I thought I'd just hit a couple of highlights. Okay? So, can somebody remind us of the analogy that I think Bryn gave us in the video last time around? There was something about a guitar. Right? How did that analogy go? Why don't we go with Madison? Thanks, Madison.
There was a guitar and then a cord and the amplifier.
Okay.
And after discussion, we decided that there was an effect with the amplifier.
Okay. Wow. Good. Yeah. Put all that together, right? So we say that if we're having some problem with our sound system, and you're the sound person, you're the sound engineer, it might be that the problem could be originating at the stimulus itself, which would be the guitar, right? Or it could be the case that the problem is originating in the connection between the guitar and the amplifier, right? So the connecting cord. And these would be down here, the bottom of the visual system would be akin to the guitar. That's where we have the transduction occurring, right? And then we have the connections. You might think of that as something like, very rudimentarily, you might say it's the optic nerve, but it also can be any number of connections, optic radiations, that connect us maybe to the brain, and that's going to be akin to the amplifier. And Madison already gave us a take-home message, which is that we had a limitation at the level relatively late in the visual pathway, not in these early levels, and not in the connection also. So who remembers that analogy? Did that all sound familiar? Okay. All right, so we have this going on in Figure 2. We had a simple variation going on in Figure 3. I'll try to keep this at the level of figures, okay? And we have something like Figure 2A shown here for Figure 3, and then we just added one other new stimulus. And the analogy that we gave here was, who remembers that we did the color After Effects demo, and we had you look at one particular stimulus, but then we changed your eye position, right? We had to look up and down, and we're basically giving you the same stimulus, but we're now stimulating fresh neural tissue, right? So a different part of the eye is being stimulated. People okay with that? Right? And what's cool about that is, let's say that you're running a test, and you figure out that maybe the limiting factor is not coming from here. Maybe the guitar is just fine. Maybe the retina and the early visual pathway is just fine, but the limiting factor might be happening at some point after that, okay? Maybe in the connections, maybe at some later stage, late in the brain, okay? That might be going on. By doing this, by introducing a novel stimulus on your retina, we can run a line back up to the same task of interest, the simultaneity task, and now we can see, do we get any change in performance now that we've changed the input? Okay? Because if we find that, for example, in a learning situation, if we're getting better on this simultaneity task, okay, it could be the case that the reason we got better is not because of this, but rather because of this or that. Right? It could be that the improvement was made either in the connection, you've got a better chord, or you've somehow improved your amplifier. So now if we introduce a new stimulus over here, and we run, if you will, a brand new line, if we still show that the learning has transferred over to here, then that would implicate this particular box, and that's very consistent with what Madison just shared with us, that the learning had occurred very late here. This had been the limiting factor all along. Okay? So hopefully that's a little bit clearer. And just to give you another idea about how we changed the retinal position, I'll go to some of these diagrams. See if I can make this really large. And what I'd like you to take away from this diagram is you might be able to tell that these top guys and these bottom guys are not straight up like this. They're tilted a little bit like that. Do people see that? They're tilted. So we actually started out with the idea that we were going to have, you're fixating here, 1, 2, 3, 4, just nice and centered. But we tilted them this way while you were training, okay? And then later on we're going to try for a transfer test, and we're going to tilt them just the other way. So we're putting them into new retinal positions. This is retinal position 1, and you're going to be doing lots of training on that if you were one of our participants, okay? And then we want to see if it transfers to a new retinal location, and we go over to this side, and I have that somewhere in here as a diagram. You can see these are tilted a little bit clockwise from vertical. Are people okay with that? Yeah, okay. And then if we go back over to here, and there's our clockwise tilt. And at some later point, I might show it in diagram. I'm not sure if I have it in diagram. Now they're tilted in the opposite direction. They're tilted this way. People seeing that? Yeah, that the overall skew is that way. And that's our simple way of getting back to figure number 3, where it's the same old test. We're still going to be asking about simultaneity, but now we're getting a slightly different bit of retinal tissue that we're stimulating because we're testing these bits rather than those bits. Who's okay with that? Okay. So same task, you're still making simultaneity judgments. You have to say whether things happened at the same time or a different time, but now we're running up a new guitar with its own new its own new connecting device into the same old amp, and we are going to show, in fact, that the training does generalize. Okay? Okay, so just to remind you a couple of other quick items. Let's go to figure 8. I'll give you a highlight on figure 8. And these were some data. Okay? A lot of data here. What we're hoping to show you in this particular case is evidence from figure 8 for what we would call task specificity. Okay? That is, when you trained on the timing task, the temporal task that we have, you're making same different judgments about whether these are coming on at the same time or different time. We get better. D prime is going up, and D prime is going up, and that's true whether we're in the left visual field or the right visual field. Okay? We're going up here, but we're really not getting better on the spatial task, even though the stimulus is the same. Are people okay with that? Is that working for us? Okay. So what's cool about that is that alone tells us that what was getting better during training was not this early bit, because if it were something very early, like your retina or something very early in the visual pathway, that would have improved everything downstream. It would have made an improvement over here. But this improvement turns out to be not statistically significant. These are. Okay, so something after that early stage, something after the guitar, must have improved with training. And it could be either the connection or it could be the decision stage. And then we come down for the very last data slide. So the take-home message from figure 8 is task specificity. Okay? And the take-home message from figure 9 is that we have generalization across retinal locations. So we have a prior location shown here in gray. We have a brand new retinal location. Here was the old location where you trained. Here's the new one. You're statistically indistinguishable. You're actually a little bit better at the trained location, but not statistically so. Okay, so we got better at all locations, but on a task-specific way. And that pattern implicates this very, very late brain area that is going to be picking up timing issues in your right visual field, and that's where the problem appears to be. So Madison had that just right. Who's okay with all of that? Yeah, okay. So sometimes when you hear it a second time and we're fresher in the day, it comes back a little bit more clearly. Okay, that's about the level of detail that we would need. What I would like to ask is question 15 from that TED Ed, which was something about metacognition. Is there something that now remains unclear to you? We want you to think about your own thinking, right? And I would be happy to go over any portion of what we've just described today. But maybe it's clear, maybe it's not clear. Yes, please, go ahead.
So, the guitar is the stimulus, the chord is the connection between them, which is called the optic nerve and optic radiation, like the light gets to it. And then the amplifier is like a later level in the visual pathway. Can you define that?
Can I define a later level?
Yeah.
Sure. Okay, let me give you a relatively early level. A relatively early level, and that's really what this first one was, if I can dial back to figure 2. A very early level in the visual pathway would be your photoreceptors. Okay, they catch the light. They do the transduction for us. Okay, they do the cis-trans isomerization. Slightly after we catch the light, we have ganglion cells, but we're still in the retina. Remember, the retina was no bigger than a postage stamp. So we're still in the retina. That's still early-ish. The next major stop, maybe you can tell me, after we go out through the optic disc, which gives rise to the psychological phenomena of the blind spot, we now go along to another stopping point. What's the next stopping point after the retina? Does anybody recall? Big nucleus. Yeah. The LGN, the lateral geniculate nucleus. Okay, so that's a little bit later. And then a little bit after that, we can make it all the way back to the primary visual cortex. So that's still, now it's getting a little bit later, but it's still relatively early-ish. And then after that, we might have things that are, we might have activity recorded in the parietal lobe. And then after that, we might have frontal lobe activity. Is that also, like last Monday's session, right? We talked about really late portions of visual processing happening up here in the prefrontal cortex. That's going to be, you know, really, really late. And the parietal lobe would be a little bit earlier. Visual V1 would be a little bit sooner than that. The LGN inside of the thalamus would be a little sooner than that, right? So does that give you some idea about what's early and what's late? Great question. Some other questions about anything that's unclear there? Okay, good. So let's now get into talking all about audition. And we have lots of things to talk about here. First, can we do this? We haven't done it in a while. Can we do the wave? Okay, so let's do both waves. We're going to do a transverse wave. What does that mean again? The transverse wave? And then we'll do a longitudinal wave. Okay, there we go. Some people are doing the transverse. So that's going to be the light wave. Right? And then we'll do the sound wave. So transverse first. Okay? And here we go. All right, that's that. Okay, now can we do the longitudinal wave, and that'll be the sound wave, so we'll get into position for that. Good of you to remember. People are, okay, really cool. And if you will, metaphorically, wait for the person next to you to hit you. You actually don't have to be hit, but almost to hit you. So here we go. Oh, it's low, and then we're coming back. Okay, wait for your partner to almost hit you and back. Right? Okay, so very good. So now a wave is a traveling disturbance, and we know that we have local oscillations, and we have this sort of macro-level oscillation. So the wave is traveling from left to right. In a longitudinal wave, the local oscillations are parallel to the overall propagation. And if in the transverse case, they're perpendicular. So you're going up and down as the wave is going left and right. Okay. One other bit that I wanted to see if we could chat about before we got into all the details about sound. Can somebody remind us of the relative speeds of sound versus light? So maybe you know the speed of sound. I mentioned it in the video. Speed of sound. Tony's got it? 343 meters per second. Thank you, Tony. That's spot on. 343 meters per second. And there are some caveats on that. I think it depends in part on barometric pressure and so forth, but 343 meters per second is the number that we're going to use. Can somebody help me out in expressing 343 meters per second in scientific notation? Who's heard of scientific notation? Yeah? Okay. So, and we haven't done it before, but most of us do this in high school and other science classes. It doesn't come up that frequently inside of psych, but occasionally. So we want to put 343 meters per second in scientific notation. Anybody want to help us out? Yeah, no one's got it.
3.43 times 10 squared.
Times 10 squared or to the second power, right? So the idea is, because that's a 2, I can move this once, twice, and we'd be at 343 meters per second. Who's okay with that? Okay, so as I'm speaking to you, my voice is coming to you at 343 meters per second. Okay, or that's a pretty good approximation. Can somebody float us an approximation for the speed of sound? I'm sorry, speed of light. Wait a minute. Speed of light. This is the speed of sound. Right. An approximation may be expressed in meters per second if you know it. And I don't think I mentioned it in the video. We'll go with Zach. 3 times 10 to the 8 meters per second. So we're this first coefficient, if you will, is pretty close. And actually, I'm not sure what the digits are here. I think it's 2.999 and something, but we'll call it 3 times 10. And can you float me the exponent again, Zach? To the 8th is exactly right. Okay, so that's going to be light. Huh. Okay, so those numbers are quite different from each other. Okay, right? Can somebody express how they're different from each other in terms of magnitude? So what is that? Go ahead, May.
Light travels a lot faster.
Light travels a lot faster. Can we begin to quantify that? Well, forget about this little ditty. We'll say that's close enough for jazz, right? Close enough for rock and roll, all right? But those other guys are very different. Yeah, so how does that?
Well, 10 to the 8th, you can just kind of think of it as adding just 8 more zeros.
8 more zeros.
So just 2 more zeros, so if you multiplying 3 by
10 to the 8th, you're going to get a very short, small portion of a second versus 3.43 times 10 to the second.
Yeah.
A larger, like meter.
Oh, okay, so here, yeah, smaller meters here, okay, all right. Somebody else have a way of expressing that. That was nicely done. Yes, thank you.
About a magnitude of a million.
Thank you for saying that. And they're both saying the same thing, and I like this conceptualization also. So Zach is pointing out that there's about a million-fold difference. And when I say about, the difference is maybe, right about here. But if we just look at these, there's a million-fold difference. Zach, can you just give us a reminder of how that's exactly right? How did you get there?
I mean, since I just approximated both 3 and if you divide 28 by 10 seconds, you get 10 to the 6.
Okay, so who remembers that trick? It's been a long time. For many of us haven't done that in a long, long time. But if you begin dividing exponential phrases, you can simply subtract the exponents one from the next. So if you have something like 3 times 10 to the 8th, and you want to divide that by 3 times 10 to the second, the trick there is simply to subtract 8 minus 2. And 8 minus 2 is? Okay, that's my kind of math. I like to have that kind of math. 8 minus 2 is 6, but that's actually 6 log units or 6 orders of magnitude. They use those terms interchangeably, a log unit or an order of magnitude, which means a factor of 10. And that means, as Meg was pointing out, how many zeros we've got going on there. Okay? So I like to, this is a fun day for putting these things into some context. And some people have already done this maybe in other classes, maybe in physics classes and so forth, but to put that difference into context. Does anybody know roughly what the circumference of the Earth is? We can look it up. Does anybody happen to know it, the circumference? Let's go to Google and look up circumference of the Earth. But do you, okay.
24,901 miles.
Okay, so you beat me to it. 24,900 miles. Okay, so about 25,000 miles to a person. Okay, and what's the conversion factor to get to kilometers? That's miles. 25,000 miles. And by the way, does anybody know the speed of light in miles per hour? Or miles per second, I should say. Yeah. 186,000 miles per second is what that thing is doing. Right? So here's a rough approximation. One of the ways of thinking about this, right? We have a million-fold difference. I think I calculated that every second, and I could turn on a metronome, and we could put it at 1,000 to 1,000. We could put it at 60 beats per minute. That would be once every second. Okay? The speed of light could travel around the fat part of the Earth, the equator, 10 times in 1 second. Right? It could do that 10 times in 1 second, or nearly so. Maybe approaching 10 times. Whereas in that 1 second, it would be the case that the speed of sound could travel across Deed's field. Okay? So here's Deed's field. Does that look familiar to people? Okay, and so the football field itself would be 100 yards. If we go to we include the outer boundaries here for the end zones, that gives us a little bit more. And then maybe we'd have to go to, that's 300, that's 100 yards. So we have to go maybe here, there, and there. So we can go back and across this thing like maybe 3 times in 1 second for the speed of sound. But it would be 10 times around the entire circumference of the Earth for the speed of light. And that's what we mean by a million-fold difference. Okay? Who's finding that pretty dramatic? Okay, all right. So many fewer times across Deed's field than around the circumference of the globe. All right, so we're dealing with a slower medium here, which I think is pretty cool. All right, any questions on any of that so far? So our first of the extraordinary number sets. We have a couple of other extraordinary number sets coming up. Yes, please. I actually haven't done it. I see that they make the transverse wave, but they say the letters around the stadium, okay?
I feel like they enjoy it, so they do.
Maybe we'd have it on video. I will find it now, but
I probably do. It's funny from one side of the stadium to the other. You see them react first, and then like a second later you see them say the letter. So
okay.
Enjoy it.
Well, yeah, we all have that experience, right? Where you see somebody chopping wood at a distance, and you can see it, and then the sound catches up, right? So yeah, pretty interesting. Also, that probably for most of you right now, as you're watching my mouth as I'm speaking to you, you don't get any kind of mismatch. Interestingly enough, that is to say that how many people are having the experience that there's pretty good synchronization between the movement of my mouth and what you're hearing? Is that okay? Have you ever watched a television show where they go out of whack a little bit, and this person's speaking, and then the sound is behind her, and it's a little bit disconcerting. But what's really cool is that as you're watching my mouth with your eyes, that information is coming to you at this speed, whereas the information coming to you auditorily is coming at this speed. Okay, so the light is actually hitting your eyes 1,000,000 times faster than the sound is hitting your ears. Who's okay with that? Okay, and yet somehow it all looks the same because we have a lapse in simultaneity. Okay, that is to say that those two, even though they're actually different physically, they're landing within a certain window of integration. And if things happen inside of that window of integration, even if they happen at different times, you perceive them as happening at the same time. It's almost as if Bryn has gotten to the bus stop at 1:40 and Rachel has gotten there at 1:50. They're 10 minutes apart, but they both make the 2 o'clock bus. Okay? So as long as we're within a certain window of integration, your nervous system can make those things seem simultaneous, and you psychologically perceive them as simultaneous. But we know from physics that it can't be the case that the light that's bouncing off of these lights, my mouth, and into your eye for the cis-trans isomerization, that's happening, that external part is happening 1,000,000 times faster than the sound is. But it doesn't seem like I'm out of sync. Yeah? People okay with that? Right? And that asynchrony only becomes really obvious when we start pushing, as Claire is suggesting, we start pushing the distances. And now you're looking all the way across the stadium, and you see the signal way before you hear the signal. Right? Pretty cool. Okay. All right. Let's get into some of these. Okay. I think I asked you to draw some of these diagrams. How many people are okay with that? We have an amplitude difference here. Is that working? Everything else is the same, right? So they're starting at the same relative position, so the phase is the same. We get a peak that goes here, and here, and here, so we have the same wavelength for each of those, right? Which aspect of FAPO is missing from this diagram? Which aspect of FAPO is missing here? Go ahead, Claire. Orientation, right? We've got FAPE. It's a little bit out of sequence, but hopefully you can make a connection between FAPO from the last section in vision. Now we're getting into audition, and there really is no orientation to speak of, right? I mean, this is vertical, this is horizontal. That's all visual information. It's hard to, if I were to turn this way, just like you probably wouldn't tell if your eyes were closed that my voice had changed anyway, right? So the sound is relatively orientationally invariant, but that's not true generally for vision, that's true only for audition. So we're dealing with 3 of the 4 characteristics. Okay? Okay, and we can talk about where intensity comes from. I wonder if somebody can walk us through the difference between a compression and a rarefaction. Somebody help us out with that. Jess has that. Thank you, Jess.
Compression are areas that have high pressure, so there's a high number of air molecules that are in space, where the
Rarefaction, yeah.
are low pressure, so there's a low number of molecules that are in space.
Okay, perfect. That was just spot on. A moment ago, we did the longitudinal wave. Jess, could you help us out? During that demo, what would have been a moment of rarefaction and what would have been a moment of compression? During the demo, everybody's hands out like this. If we're not sure, that's okay. Can we do it one more time? Can we put it out our hands and we'll do just a portion of it? And I'm going to ask you to freeze mid. So let's do 1 or 2 waves, and I'm going to ask you to freeze mid-cycle here. Wait till you get hit by your partner. And coming back. And can you freeze? Okay. Compression or rarefaction? Okay, and then a moment later, the movie is back in play. Okay, and we're going to look at those same 2 molecules, compression or rarefaction? Rarefaction. Okay, we all right with that? And we can talk about how tightly packed those are, and we can measure them in a special unit. What is our unit? Anyone remember the unit of pressure? Pascals? Pascals, yeah. Yes, please.
Question. For compression and high pressure, does that mean that we're going to see higher pitches during compression than lower pitches during compression?
Well, that's a very good point. No, so that's it's similar to that. Actually, I would put it this way: we're the more compressed the air is, and we can actually let's go ahead 1 or 2 graphs. Okay, people okay with this? Yeah, is that working for us? Okay, so here Claire and Melanie's hands were together, and then here they're apart. Okay, and that's going to be happening a whole lot of times. When I play the A above middle C, I think I've played that a couple of times. What I find fascinating is that Melanie and Claire's hands are going in and out 440 times per second. That's the A above middle C. Isn't that weird? That's what's happening on your ear. right? It's as if Melanie and Claire are going 440 times per second in order to get the A above middle C. Now let's get back to Meg's question. Somewhere in here I need to get to, let me go backwards. Okay? What I'm not showing you here is what's labeled on each of the axes. So what is on the x-axis here, presumably? Time, okay, right? And what we're having here is, you might think of this as air pressure, where these are compressions and these are rarefactions. Is that working? And so if they're really, really, really compressed, they're way up here. And our psychological correlate of strong amplitude is going to be loudness. Okay? Your question a moment ago was, does that relate also to whether we hear it as high or low? And that's going to speak to the issue of the frequency of these wavelengths as opposed to the amplitude. Okay? Right? Let's pick up on that. It's a fun issue now that you've mentioned it. So if I have a higher frequency, does that sound more like a tuba or does that sound more like a flute? Yeah, okay. Higher frequencies can sound more like a flute. Okay? If I have a higher frequency, and this hadn't been longitudinal waves of sound, but they had been transverse waves of light, and they had a higher frequency, it wouldn't sound like a tuba, it wouldn't sound like a flute, it would look a particular way. What do higher frequency wavelengths look like? Does anybody recall? Yeah, higher frequency dialing, yes. Yeah. Okay, but we don't, so how do we experience those psychologically? Yeah.
Like blue?
Blue, there, okay, Abby's got it, right, so that's blue. So it's really interesting that over here in the world of hearing and the world of sound, as we get higher frequencies, we hear things more like flutes, lower frequencies are going to be things more like tubas. If we go up and down with frequency in light, then we're going to be, higher frequencies will be blue, lower frequencies will be red, okay? So it's almost as if those two are the counterparts to each other. Right? It's almost like hue is the counterpart to pitch.
So amplitude is kind of like loudness,
and
frequency is more the pitch.
Yes, that's exactly right, okay? And it would also be the case that amplitude over in the domain of vision would have been brightness. Okay, so a really bright light would be analogous to a really loud sound. Okay? Great questions. Really great questions. Okay, we're doing okay on time, but I really want to get into this question. I love this. Okay, so we did this guy. People are understanding this. We see that Melanie's hands and Claire's hands are coming together. Okay, and we have this whole thing. I wanted to get to the Volkswagen thingy. How many people gave that a shot? The Volkswagen. Okay, so we have a 15 log unit. Here's 2 log units. Here's 8 log units. Where you have a 15 log unit range that your system can respond to biologically. And what I mean by that is, at some really soft level of air pressure, your system doesn't respond. It's sub-threshold. By the way, the interesting word for threshold in German is Lyman. And if you're under the Lyman, you're sub-Lyman. Subliminal, subliminal. Has anybody ever heard the phrase subliminal? Okay, that's the etymology of that word, the threshold. So if there's a really, really soft pitch, you're not going to hear it. Right? A really soft tone, you're not going to hear it. But at some point, you begin responding, and then you can respond more and more and more as there's more intensity, and you can respond over a 15 log unit range, right? A 15 log unit range of intensities. Okay, so let's see if we can now get to this and see if anybody has a solution. What we're going to try to do is give us an appreciation for how big 15 log units really is. Okay? It's a big, it's 15 zeros, but how big is that? So we're going to try to create this scale that makes it obvious to us by analogy. And we're going to make the scale have some different weights on it. On the one end, we're going to have the softest sound that we can hear analogized by just one thumbtack that weighs 1 gram. Okay? And then over on this other side, we're going to have the top of that scale 15 log units up, 15 log units heavier than 1 thumbtack. And that's what we're trying to do here. So anybody want to help us out with how many Volkswagen Beetles they got? We have 1 thumbtack over here. Go ahead, Liz.
I'm not sure if this is right, but okay. I had 740 repeating 3 times.
740 repeating 3 times.
And then 0.741, but you can have 0.741 of those beetles.
Okay, so I think 740 I like a lot. That's going to be really good, and we'll see if we get all those. Yeah, go ahead, Meg. What do you have some?
7,407,407,407.
Okay, I think I got all of that. So So more roughly, how many Volkswagen Beetles?
So 7,407,407,407 Beetles.
Okay, I think that's too big. All right, but thank you for saying that. Okay, so here's what this car weighs in grams, and we could move the decimal point over to get to kilograms if we needed to, right? Okay, let's see if we can do just a little bit of math here. How many people had a different number? Okay, what did you get, Alexa?
I had 740 million.
740 million. That's exactly what we're looking for. I'm not sure if that's what I was hearing a moment ago. Let's see if we can just run through that lickety split. We have time to make it through. Okay, so here's how we would do that math. Okay, we're trying to figure out how many Volkswagen Beetles. So let's just start out with this. This is the number of grams that we have, and we can express it this way: 1.35 times 10 to the 6th. Okay, so all I've taken was that number, which Zach reminded us a little while ago that we had an order of magnitude of 6 corresponds to 1 million. Is that working for us? Okay, so 1.35 times 10 to the 6 grams, and we're going to take that big number. This is the full range that we have, and we're going to divide it by the number of grams that go into one particular Volkswagen Beetle. So we have a 15 log unit range that we can hear over, right? 15 log unit range of intensities that we can hear over, and we're going to try to ask how many times can we divide a Volkswagen Beetle into that range. That is what we're getting to. So here's 1 divided by 1.35 and 10 to the 15th, 10 to the 6th. So if we take advantage of our laws of logs, we're going to do 15 minus 6. Are people seeing where that's coming from? Because we have the same base, so we can subtract the exponents, just like Zach did a moment ago. And we have 15 minus 6 is what? 9. Okay, so let's see if we can get that up here. Okay, so same thing. 1 divided by 1.35, 10 to the 9. Who's with me so far? Okay, all we've done so far is 15 minus 6. Okay, and then I like that several people in the room got this far, right? Okay. And so we have 0.74 times 10 to the 9th. We can smooth that out just a little bit. We can take away one of those and move this over a bit, okay, just by 1, right? So now we have 7.4 times 10 to the 8th, and so now we have all of that 740 million Volkswagen Beetles is what that worked out to. So our scale, if we could hear weights, it would range from 1 thumbtack to 740 million Volkswagen Beetles. And that's our second extraordinary number for okay? Who's following that? Okay? Now, just to make sure that we all appreciate that, I do want to take a moment and see if we can understand 740 million, because you know that's a big number, but we don't always know how big that is. So I want you to think about us having a scale in this room, and over here on this scale, on this side of the scale, we've got the thumbtack, and then we have Meg drive a Volkswagen Beetle onto this side. Okay? That's 1, and we need 740 million of those. Okay? So then Zach drives one up. Okay, Jake drives one up. Sibel drives one. We have everybody in the room drive one up. Okay, we're still nowhere near there. And what is the population of the U.S.? Can we get somebody to check us out on that roughly? About 300. Sorry, that's right. About 310 million approximately. We'll have a fact check if anybody wanted. About 310 million or something like that. 320 million. Okay. So if every single man, woman, and child did this, okay, they all drove that up, we'd be about half the way there. Every single man, woman, and child in the U.S. drove up a Volkswagen Beetle and put it on top of the one that was there a moment ago. Okay, we'd be about half the way there. Okay? Then what we need to do is make a second round. So we say, okay, that's everybody in the U.S. Meg, why don't you drive your second Volkswagen Beetle on top of that? Okay, so now everybody has to drive 2 Volkswagen Beetles and stash those up. That gives us now, we could get up to 740 million Volkswagen Beetles doing that. Versus, on this side, what did we have? 1 thumbtack versus 740 million Volkswagen Beetles. That's the range of intensities over which your system can respond. Okay? Pretty impressive. I find that mind-boggling. Yes, please.
What's the difference between like a 15 log range of pressure and a 15 log range of intensity?
Of intensity, yes. Okay, so, and that's a good question to end on. So let's see if we can. Does anybody remember the little mnemonic that we had in the video that relates P to I, pressure to intensity? Maybe Jess has something. Yeah, P squared is equal to I. Okay? P squared is equal to I. So I is, if you will, Zach, the bigger unit. And so this is 15 log units range of the bigger of the two that we could have been measuring. Okay, so it's P squared is equal to I. And of that bigger unit, we have 15 log units of those. Okay? All right, we're just about out of time, and I do like to start on time and end on time. So I'm looking forward to Wednesday's session. We'll finish off this. We have a few more slides to do here. And then we'll also get into the physiology for Wednesday's TED Ed. All right, thanks everybody. Great session.